Welcome to the problem of the week for week 8, the product of sines. We're going to show how you can manipulate some roots on the complex plane, and by doing so find something that is truly amazing. So let's start off with our identity. We want to establish the following identity. The product of sine of pi over n, sine 2 pi over n, sine 3 pi over n, all the way up to sine of n minus 1 pi over n, which is the angles from 0 to pi, or 0 to 180 degrees, evenly spaced, and I'm taking n of those, or n minus 1 of those angles. And I'm going to take the product of the sines of all those different angles, and the claim is that the product of all those guys is just equal to n divided by 2 to the n minus 1, which is a pretty remarkable identity. So we're going to start by first finding the roots of 1 minus z to the n equals 1. And to do that, I'm going to find the nth roots of unity by taking 1 over n of that equation, and then 1 minus an nth root of unity will equal z. And so we get zm is 1 minus e to the 2im pi over n for 0 less than or equal to m less than or equal to n minus 1. And you notice that when m is equal to 0, then e to the 2im pi over n is equal to 1, and one of those roots is equal to 0. And so what we want to do is we want to focus on the remaining roots, because when we multiply anything by 0, of course, we get 0. So we're going to look at the products of the remaining roots, and we're going to notice that the m and the n minus m roots are complex conjugates of one another. So we can pair them together. So when we look at this product of all the different roots, I can pair z1 with zn minus 1, and it becomes mod z1 squared. And I can pair z2 with zn minus 2, it becomes mod z2 squared, and z3 with zn minus 3, and it becomes mod z3 squared, all the way out to zn minus 1 over 2 quantity squared if n is odd. Or I have one left over, which happens to be a real number, which is 2 when n is even. That corresponds to the root where m is equal to n over 2 for n an even number. And then I get 1 minus e to the I pi, which is just 1 minus minus 1, which is just equal to 2. So we have these two different cases that are going to come out, but that ends up just being the modulus of the z of n minus 1 over 2 in that particular case. Okay, so we've got this product, and now let's actually evaluate what it is. So the modulus of 1 minus e to the 2im pi over n, that's going to give me a 1 minus e to the 2im pi over n minus e to the minus 2im pi over n plus e to the 2im pi over n times e to the minus 2i pi over n. And that becomes 2 minus 2 cosine 2m pi over n. So please be sure you can do that algebra. It's a fairly simple algebra. I just take z times z star, and I use the definition of what a cosine is, and I can get that result. And now I'm going to use the half angle formula for the cosine, and I'm going to write cosine of 2m pi over n as cosine squared m pi over n minus sine squared m pi over n. And you see I'm going to get a factor of 2 sine squared coming out of that, so the net is going to be 4 sine squared m pi over n. And now I have to notice that sine of m pi over n is equal to sine of n minus m pi over n, which is an identity you can easily verify by using the angle formula for the sum formula or the difference formula for sines. And so it looks like each one of these terms is giving me a factor of 2 sine m pi over n. So what we found is the product of all of these roots, except for the root that's equal to 0, is going to equal 2 raised to the n minus 1 power times the sine of pi over n times the sine of 2 pi over n times the sine of 3 pi over n, all the way out to the sine of n minus 1 pi over n. And so we're going to get all of those different terms in this net product that we are looking at. All right, that's very good. That looks a lot like the identity we're trying to establish. How do we finish the identity? Well, we have to look at this product from a different perspective. We have to note that the equation that we found the roots for, we can actually factorize. And so 1 minus z raised to the nth power is actually equal to minus z0 minus z, z1 minus z, z2 minus z, all the way out to zn minus 1 minus z, We have to remember that z0 was equal to 0, so this just becomes z times z1 minus z all the way out to zn minus 1 minus z. And now what we want to do is we want to look at the coefficient of z in this expansion. So the coefficient of the z term is actually given by the product of all of the non-zero zm's. But we also can calculate the coefficient of the z term from the left-hand side. It's going to become minus n, or n, and that's the final piece of the identity. So we set 2 to the n minus 1 times the product of all these signs equal to n. We divide both sides by 2 to the n minus 1, and that yields the identity that we have. So this is the way that you can derive that identity. And just to really give you a notion of how really cool this identity is, we're going to evaluate it for a couple of different n cases. So if I pick n equals 2, I get sine pi over 2 on the left-hand side, and that just equals 1. And I get 2 divided by 2 on the right-hand side, which also equals 1, so that checks out. If I look at n equals 3, I have sine pi over 3 times sine 2 pi over 3. Well, each of those signs is equal to root 3 over 2, so the net is equal to 3 over 4. And if I plug in n equals 3, I get 3 divided by 2 squared, which is 3 over 4, so it works again. If I look at n equals 4, I get sine pi over 4 times sine pi over 2 times sine 3 pi over 2. And if I work out what those are, that's 1 over root 2 times 1 over root 2. The net is 1 over 2. Now let's compare that with plugging n equals 4 onto the right-hand side. That becomes 4 divided by 2 cubed, which is 8, so I get 1/2. And so indeed you see that it works again there. Let's check out n equals 5. I get sine pi over 5, sine 2 pi over 5, sine 3 pi over 5, sine 4 pi over 5. Now you might have not known this, but there actually is an explicit formula for sine pi over 5. And I can then compute sine 2 pi over 5 from the double angle formula for sine, and then I can compute or notice that sine 3 pi over 5 is the same as sine 2 pi over 5, and sine 4 pi over 5 is the same as sine pi over 5. And so I get this product here. And now you notice if I multiply the first two terms and the square roots together, I will get 100 minus 20 under the square root sign, and that becomes the square root of 80. But I have the square root of 80 from the last two terms as well. So the net effect is I get 80 in the numerator, and then I have 4 factors of 4, or 4 raised to the 4th power, or 256, as the denominator. I can divide out a factor of 16 from both. I get 5 over 16. Now let's plug n equals 5 into the formula. I get 5 divided by 2 raised to the 4th power. Well, that just is 5 over 16. So miraculously, again, this formula works. And we'll do one last case. We'll look at n equals 6, sine pi over 6, sine pi over 3, sine pi over 2, sine 2 pi over 3, sine 5 pi over 6. So that becomes 1/2 times root 3 over 2 times 1 times root 3 over 2 times 1/2. That becomes 3 over 16. If I plug 6 in, I get 6 divided by 2 to the 5th. 2 to the 5th is 32. And indeed, that equals 3 over 16. And I can complete going on with this and verifying this identity. And I don't know about you, but I just think it's really a remarkable identity, and it simply follows by looking at the roots and doing some manipulations with complex variables that are manipulations that you can do, and also remembering a little bit of the trigonometry that we need to remember about half-angle formulas, double-angle formulas, and other things like that. And that then concludes the problem of the week for this week.